Log on, tune in, find out. Another good idea from Cambridge.
There's Pixton from Princeton, who's going to tell us about the stable pair theory of local curves with stationary descendants.
Okay. Thank you for inviting me to speak today. This will all be joint work with Rahul Pantarapondo. So I'll start just by giving the basic setup for stable pairs theory. I'll be talking about specific case of local curves with stationary descendants, but in general we have X is non-singular threefold, beta is a curve class on X, should be non-zero. And then moduli space of stable pairs. So this is denoted Pn of x beta. And here is some additional integer parameter. A point in this moduli space is a morphism OX to F, where F here is also a sheaf on X. And just a few conditions, F should be a pure sheaf. That is, its support is one-dimensional, and the support of any non-empty subsheaf is also one-dimensional. And some numerical data should have Euler characteristic n, and the scheme theoretic support of F should be this curve class beta. And this section S should have zero-dimensional co-kernel. So this moduli space should be thought of as very closely related to, say, the moduli space of ideal sheaves, Donaldson-Thomas theory. Since you have a curve and you have some additional data on the curve, in this case you have this sheaf on it with certain numerical data, which in the sections can be thought of sort of as generically you are choosing a Cohen-Macaulay curve and a Cartier divisor on it. In comparison to Donaldson-Thomas theory, the one way of thinking about difference is that here you can't have like points wandering away from the curve. Everything is actually on some curve. So moduli space stable pairs has a perfect obstruction theory, and you can get a virtual class satisfies all the properties you usually want. This is just some cycle in the Chow ring. And this class has dimension given by pairing the first Turing class of threefold X with the curve class beta. So in particular, if we were in the case X collab this would always be virtual dimension 0. And so then you would immediately have integer invariance given by counting points on this 0 cycle. In general, however, this virtual dimension is going to be non-zero. So in order to actually translate this virtual class into numerical data, it's useful to have descendants that you can hit this with to change the dimension of the class. So I'll briefly describe the definition, how these descendants are defined. Which is a little bit more subtle than, say, in Gromov-Witten theory setting, where the descendants are actual cohomology classes on the moduli space. Here, they're operations on cycles on Pn. So to define this, this is a whole moduli of sheaves, so we have some universal sheaf. F on x cross p and x beta. And the idea is that descendants are going to come from taking Chern characters of this universal sheaf. But since we're actually working on p and x beta, not the product, we have to do a little dance with pulling things back and pushing things forward. Along these two projection maps here. So the data parameterizing these descendants are, you have some non-negative integer I and a cohomology class gamma on X. So the descendant tau I of gamma, then, so it's the operation, we start with a cycle on p and x beta, we then pull it back to this product, we cap it with some stuff, and then we push it back forward. So just write that out. The thing we're capping with, well, we have two different pieces of data here. One of them is a class on X, which we can just pull back to get something on there. The other is integer that parameterizes which Chern character we take. And then we push it back over to p and x beta. So this is operation on cycles on p and x beta. And it's easy to see that this might change the dimension of your class by some amount. So now the game is that we have some virtual class of some degree. We hit it with some number of descendants to change the dimension of it to 0, and then we can count points of a 0 cycle to get some actual number, which will be a rational number because string characters involve dividing by stuff. So these are the descendant invariants. So we have some number of these descendants. we still have the data before of our threefold, the curve class beta and some integer n. This is what I said it was. Take these descendants, you apply them to the virtual class. And then this is a 0 cycle, and we integrate 1 on it to count points. Now, something to note here, in this virtual dimension formula did not depend on this parameter n, which is just the Euler characteristic of the sheaf. So if we now vary n, keeping the descendant fixed, we can maintain appropriate dimension for everything we got. Note that what I wrote down here, if the dimensions don't work out, this is just 0. So we sum over n to get the partition function of threefold x, curve class beta, for this descendant insertion. Just sum these descendant variants with respect to n. So the definition here makes sense for n being any integer, but in fact it's easy to see that if n is sufficiently negative, then this moduli space Pn x beta will always just be empty. So this is actually a Laurent series in Q. And the fundamental conjecture about this, due to Hunter, Panda, and Thomas, is that this partition function is always Laurent series expansion of a rational function of Q. I'm just going to abbreviate that to say is in Q. So this conjecture is known in certain special cases. For example, it's known in Calabi-Yau setting when all your insertions are primary field insertions, all of the i's are equal to 0. It's also been known for a while to be true for toric X if all of the, again, primary field insertions case. Some recent work that I'm not going to be talking about with Rahul again is that this conjecture is true with arbitrary descendants in the toric case. That requires some fairly detailed analysis of the equivariant descendant vertex. But there's some, and a related note to that is that this is also true for local curves, which is what I'm going to be talking about here. Specifically, I'm talking about the case where x is a local curve and all descendants are stationary. So first, by local curve, I just mean, so before x was an arbitrary threefold in this conjecture, but local curve is a very special case where x equals total space of some split rank 2 vector bundle L1 plus L2 over some non-singular curve C. And here, beta, the curve class for such a threefold, this just corresponds to choosing a degree along the curve part of it. So this is some degree d greater than 0. So I'm going to be interested in talking about a relatively simple way of handling the descendants in this local curve setting and handling only the descendants which are stationary. So stationary here stationary just means that this will be tau I of a point class. So think of this as pinning down some points that the curve has to pass through. Okay, so before here I was stating the stable pairs partition function and the conjecture of rationality in the general setting for arbitrary threefolds. But it's natural in this local curve setting to consider, well, first to consider the equivariant version of this. So local curve X has a 2 torus acting on it. That's just by scaling the 2 factors L1 and L2. I note, in fact, that if in certain cases it might even be toric, have a full 3 torus action on it. For example, the simplest local curve you may imagine is C cross C cross P1. But generally you have a 2 torus acting on it, and this, if you keep track of this 2 torus action through the entire process and work in equivariant cohomology, then at the end, these invariants here will not just be rational numbers. They will be rational functions of 2 equivariant parameters, S1 and S2, corresponding to 2 factors of the torus action. So at the end, this partition function is the x beta. Put the t here to denote the equivariant with respect to this action of t. This will be a priori, it will be still Laurent series in Q, but the coefficients will be rational functions of S1, S2. And the natural conjecture to make, which in this case, local curve casing actually stated as a theorem, is that partition function is a rational function of S1, S2, and Q. One of the nice things about working in equivariant cohomology, so first, this is a strictly stronger statement than the non-equivariant version. You can always forget about the equivariant action to recover that information as taking some coefficient here. Another reason why this is nice is that before, I had to be careful to get the dimension to work out precisely to 0 before integrating 1 on it in order to get something non-trivial, something that isn't just zero always for trivial reasons. For equivariant cohomology, you have a lot more freedom to not worry about dimensions so much, because some of the dimensions could go into the equivariant portion of these invariants. Okay, so that's one aspect of how I actually want to consider something a little more general than just the most basic conjecture of arbitrary threefolds. I'm not going to say much about this. It'd be important to consider the relative stable pairs theory. So, in addition to x and beta, you have some non-singular divisor s on x. And considering everything relative to s, this means you're enforcing some relative conditions along where the curve, where the sheaf hits the divisor s. I'm not going to say anything about how this is defined, but stable pairs theory works in relative setting, and can define partition function x relative to some divisor s. I should say up here, because I'm doing the local curve, and switch the notation of instead of beta, I just have d. Really, beta is d times the class of the zero section of that bundle. So here, like I said, you have to put in some relative condition. Along S. And we still have this is Laurent series and Q as coefficients in S1, S2. Now for this to make sense, our choice of divisor S had better respect the torus action. So what S is actually going to be in the case of local curve. So local curve is L1 plus L2 over C. S equals finitely many fibers of this. So in the case where S is finitely many fibers, the relative conditions stipulating how this curve is supposed to meet S is the same thing as choosing some class in the cohomology of Hilbert's scheme of d points on the plane for each fiber. So I'm going to so I'm going to write this as these conditions as eta 1, eta 2, eta k, one for each fiber that we're looking relative to. And these here I'm now thinking of just as partitions, which will correspond to specific cohomology classes in Hilbert's scheme, the Nakajima basis. So yes, the way to think about all of this is we have some curve C and this rank 2 bundle on it, and certain specific fibers here S is equal to S1, S2. We're looking at for sheaves which are degree D in this direction, their support is degree D in this direction with certain fixed Euler characteristic and intersecting each of these S1, S2, Sk in the points grouped in certain ways. And player moduli space has this action of the torus on it. So again, the question is, we want to have some way of getting at these invariants. The reason why the relative theory is important is because stable pairs theory satisfies usual degeneration relations to allow one to break your threefold X and re-express invariance in terms of relative invariance on the pieces. So the goal here is we have some stationary descendants, these tau I of p, on this curve. And we want to somehow get rid of them. I'm treating in all of this the case where there are no descendants as something which is already known. In that case, as I was saying, these conjectures are sort of all known in the torque. We're all known in the torque case already without any descendants, because then there are good correspondences which allow one to translate this problem into the Gromov-Linen picture, where these things were proven. So here there are these descendants, and essentially want to describe a method for removing them. So there are two pieces. One is some degeneration arguments. The other one is a general reduction rule for descendants of high degree, which I'm going to mention. So the way this is going to work is D here is still D is fixed in is going to be fixed in everything I'm saying. It's the degree along the curve, and if k is some number greater than d, then we want to replace tau k of p by some tau I of p for I less than d. So if k is greater than d, there exists a polynomial fkd of t1 through td, just d indeterminates. The coefficients here will be rational functions f1 and f2. And then the property that this polynomial satisfies is that you can replace descendant tau k of p with this polynomial with tau 1 of p through tau d of p inserted. And this is all in degree d. So basically the reason why this reduction rule exists is these descendants were defined by essentially taking Chern characters of something. And if you work out via localization actual formulas for what they are taking Chern characters of, you can reinterpret them as certain symmetric polynomials in d variables. D variables, in some sense, correspond to the fact that we're degree d. So at any slice, we only have d points in action. So proof is simply interpret descendants as symmetric polynomials d variables. Then the first d will be some basis for the algebra of symmetric polynomials. Now, it's a little bit more subtle than that, because this reduction rule, you don't have anything like it if you aren't in the stationary case. The reason for this is essentially that if you aren't in the stationary case, then these descendants can move around. So if you tried to make some formula like this, replacing like tau k of p by some polynomial in these other descendants, and then compute both sides using localization to try to prove that, the problem is that these descendants here that you're replacing a single descendant with could split up and move apart from each other. You don't have any control over that. They could end up living on different vertices. So this really very strongly requires that we're in the stationary case. So now, how we actually are applying this reduction rule, well, we start out with just some curve and these descendants on it. Tau I1 of p, tau I2 of p, but by breaking the curve an appropriate number of times, we can choose to have all the descendants go off onto caps. So we're breaking the space curve C by bubbling off P1s and moving the descendants onto these. So this is some degeneration, and from the degeneration formula, we're expressing the invariance we got here in terms of, well, one term for each of these pieces we've added on. Each piece here looks like it just has a single descendant, and it's going to have one relative condition at the point where this P1 was bubbled off. So this is known as cap, where we have sort of relative condition on C squared cross P1. This is relative to C squared cross infinity, sorry, with just a single descendant on it. The other piece that we get is the space curve C, which might be more complicated. You should note that on these pieces we bubbled off, we can simply assume that the line bundles we have there are trivial. So it's actually C squared cross P1. We have some non-trivial stuff here, but we no longer have any descendants. So long with some more complicated looking piece with no descendants. So this reduces to invariance of the cap, where we're still in some degree D, and we have a single relative condition, eta, which is some partition again. And we have a single, it's called tau k of t, descendant. Now if we apply this reduction rule, we can break up this descendant here if k is larger than d. We might get multiple descendants in that way, but then we can split apart the descendants again by the generation argument. By using combination of this reduction rule and the generation argument, we can restrict ourselves to this case of the cap where k is less than or equal to d. So that's now a very small set of partition functions that we'd have to prove rationality for. Just k is something between 0 and d, and eta is some partition of d. We can do better. At the end of this, I'm going to reduce to exactly, for each d, exactly one invariant we have to consider. So the way to do this next step is, I'll say what the goal is. It's reduced to such a partition function where the partition is just a single d cycle. All the points are pushed together. And the descendant is the maximal degree it could be, tau d is d. So I'll say a little bit about how this reduction goes, and then I'll spend the remainder of the time talking about this very special single computation that we're left with. The way we deal with this one partition function at the end is we actually compute this explicitly. It has a nice formula. And you can see it's a rational function. So say a little bit about how this reduction works. So the idea is to compute an invariant on, well, here we had sort of C2 cross P1. Here I just want, here I want to compactify that to P2 cross P1. Again, relative to a single fiber. So compute that using virtual localization in terms of some of these capped invariants. And there will be one principal term, which is the one which is not of this form, that we won't do something with. And then there will be things which are, in some sense, closer to this form. By repeatedly getting relations in this way, that's how this reduction is going to work. So in order for this to make sense, we need some reason why we know that this invariant is rational for going to get something. Because we don't want to have to try to prove directly that some random invariant on random partition function P2 cross P1 is going to be rational. And the way we do this is by choosing the relative conditions and descendants carefully enough so that by dimension reasons, we can get that the invariant here is 0. So specifically, the relative condition. So here this will live in the cohomology of the Hilbert scheme of d points on P2. So we want to think about a partition weighted by elements of cohomology of P2. Really, we're working equivariantly through all of this. And so P2 with the usual torus action is 3 fixed points. And the idea is going to be to nail down one of the relative conditions to one of the fixed points. So then there will be only one term where all of the relative conditions stack together. All the other terms will be in some sense smaller. The relative conditions will be split apart in the localization procedure. So we started with this partition here, eta. New relative conditions are given my weighted partition so relative condition eta tilde. This is a weighted partition. Assigning the class of some point, C0, to the first part of eta, and 1 to all other parts of eta. So, and the descendants will be these, essentially the same thing we had there. If we work out the dimensions of stuff, so the virtual dimension with this relative condition imposed is turns out to be d plus the length of the partition eta minus 2, and the degree of the descendants is just k. So, this is always greater than or equal to d minus 1. This is less than or equal to d. And so this means that this invariant we're doing here ends up having degree less than or equal to 1. I mean degree in S1, S2, and S3. We have a full torus action here. And this is pretty limiting because this is actually compact. So at the end of the day, we should be getting a polynomial in S1, S2, S3. And we have the degree is less than or equal to 1. And if the degree is less than 0, then it just has to vanish. For these dimensional reasons, if the degree is equal to 0, then we can show by some other arguments that it then has to be rational functions, actually a monomial in Q then. So the only remaining case where we can't do this reduction method I've outlined to go from here to here is when we've degree equal to 1. But that's precisely when we have equality in both cases here, which means the length of eta is 1 and k is equal to d. That's precisely the one case we're left with. So the sketch of this final reduction here. Okay, so this invariant is very special. Like I briefly explained here, it has degree 1 in S1, S2, S3. And there are okay, I should be a little bit careful in that this is on the cap C2 cross P1, which is not compact, so you might worry it has some denominator. You can compactify the moduli space by considering some additional equivariant condition. Basically, you just want to, in your picture of C squared cross P1, you want to prevent movement along the C2 direction. If you take that into account, then we can show, without doing any computations, the single invariant left here, C cap D, D octal D of a point. This is going to be equal to S1 plus S2 divided by S1, S2 times FD of Q, where FD is the Laurent series in Q alone, as the equivariant dependence factors out. This is, in other words, I'm saying that this invariant is very special because it's sort of extremal in some sense, so we can say that it's of this precise form. There's still the question of what is this Laurent series here, which should actually be a rational function. And this can be computed directly. Because we're on the cap, we have a full torus action, so we can actually just try to use equivariant localization to compute this. So you get a lot of terms, of course, when you do this sort of thing. So there's one idea that we'll call some massive simplification to this computation. So what you sort of generically get from localization is a sum over partitions of D. This is an edge partition of you have a vertex term over 0 on P1, and you have some edge factor, and then there's some rubber term over the relative part. So of these three pieces, the edge factor is something very simple. It's monomial in Q, and the dependence on S1 and S2 is given very simply in terms of a representation theory corresponding to this partition. We look at like dimension of the irreducible representation of Sn corresponding to mu and throw in some other factors. Vertex term is a priori some complicated sum over certain box configurations in 3 space. And this rubber term is also not that simple. This is given by quantum cohomology of Hilbert's scheme of d points on C squared. But the way in which one can actually carry out this computation without too much trouble is by noting that the vertex term and the rubber term both are of the form, I'll write it here. Those are the form, you have some leading term which is just q to the I, and then all the terms after that are divisible by S1 plus S2. I'm just going to write that as times O of q to the I plus 1. So look, modulo S1 plus S2 squared. Because we know how the answer depends on S1 and S2, that's not losing any information to look mod S1 plus S2 squared. But because most of the terms you're getting from the vertex and from the rubber are divisible by S1 plus S2, this creates massive simplifications. Allow one to actually explicitly compute this. So at the end, I'll just write out what this is. Some initial factors times a sum r goes from 1 to d of 1 plus minus q to the r by 1 minus minus q to the r. So I don't have a particularly good explanation for why the formula is of this interesting looking form, which similar expressions to this appear in these rubber calculations in quantum cohomology, but the connection there is not direct. And finally, I'll just state that the important thing in this computation here was that for dimensional reasons, we knew that the answer was in this form. And this would also be the case if instead of just having a single descendant there, tau d, we had multiple descendants with the same total degree. So like tau m1 of p times tau m2 of p times tau m3 of p, where m1 plus m2 plus m3 equals d. And in those cases, we can also get an explicit answer, which is messier than this.
Any questions?
What do you learn about the poles?
The poles of what precisely?
Z. Once you go all the way back.
Right. So in the procedure in the reduction procedure, we're reducing everything to something with poles at just roots of unity. like this. So the only question is how much knowledge we have over the poles in the terms that I was sort of throwing away because they didn't have any descendants. These which are basically arbitrary partition functions of local curves relative to stuff. I don't remember.
Yeah, we
you
proved
remember?
it
Is this one case where we can prove it?
Yeah,
Or?
so we did finally prove that the poles for this local curve theory is always just roots of really what you expect. But actually, that proof of that is required.
You can't prove it from this.
Yeah, you
so.
can't prove it from this. It uses some different ideas, but the quantum cohomology of the Hilbert scheme of points, it's not known. It wasn't known there. We had to prove it there. It uses these descendants. But it is true. The poles are just these roots of unity, but there's not a conceptual proof of this.
I mean, we needed the result for arbitrary descendants, non-stationary descendants, to be able to do that. So this is all just when all the descendants are stationary. So as I mentioned briefly, we did prove with arbitrary descendants the rationality statement by sort of a much more detailed study of what's going on in the vertex.
But for the club, yeah, okay, so there's good conceptual reasons why it's rational. But for the descendants, it's not the case at the moment. And that polar statement is also very puzzling why it's true. But it is true, but why it's true.
Do you have it in kind of BPS form, or you just have the
It's not so
poles?
clear what the BPS form is for that. I don't know.
Or do you have Q goes to 1 over Q?
No, there isn't Q goes to much. But it's not incredibly far. I'm not surprised.
Any other questions? If not, then we thank Aaron again.